Alright, so this is our walkthrough for the assignment titled Second Derivative Test for Extrema. So what we're going to do here is we're going to use the second derivative test to determine if any of the critical values that we get from the first derivative give us maxima or minima on this function. So step one is just to take a derivative. So we'll start with f prime of x. 1/3 x cubed should just become x squared. 5/2 x squared should just become plus 5x, and then a plus 6. And so first thing we need to do is set it equal to 0 to find the critical values and check when it's undefined. We can see this one's never undefined, so we don't really need to worry about that. But it factors to x plus 2, x plus 3, giving us two critical values, x equals -2 and x equals -3. Then the second derivative test says at a place where the first derivative equals 0, check the value of the second derivative at each of those x values. So our second derivative is just 2x plus 5. Now, remember that the second derivative tells us whether the function is concave up or concave down. And if you have a nice smooth curve where we have a max or a min, because our derivative is equal to 0, if the function is concave up, it has to be a min, and if the function is concave down, it has to be a max. So we just need to check and see if the function is concave up or concave down at each of these 2 points. So at f double prime of -2, we end up getting 2 times -2 or -4 plus 5, which is 1, which is greater than 0, which tells us that this thing is concave up, which tells us we have we'll call it a local min. Right? If it's concave up, it's going to be a min at x equals -2. And then if we check it at -3, we can see we're going to get -6 plus 5, which is -1, which is less than 0. That tells us that this function is concave down, which tells us we have a local max at x equals -3. So that's going to be our basic process for each of these. Just got a couple of them here. Remember, this only works when the first derivative is equal to 0. It doesn't matter when it's undefined, right? So we can't do this at places where the first derivative is undefined. So we'll take our first derivative here. Our first derivative here, we're going to use the product rule. So f prime of x is going to be x minus 1 to the 2/3 times the derivative of x plus 4, which is just 1. And then we'll add to that 2/3 of x minus 1 to the -1/3 times the derivative of the x minus 1, which is just 1, and then times the x plus 4. And so we need to look for places when that is equal to 0. And so easiest way to do that is to probably just get a common denominator here. I'm going to rewrite this as x minus 1 to the 2/3 plus 2 over 3 times x minus 1 to the 1/3 times the x plus 4. And we'll get a common denominator, which is going to be a 3 and an x minus 1 to the 1/3. And when I multiply by the x minus 1 to the 1/3 up there, x minus 1 to the 1/3 times the x minus 1 to the 2/3 should just become x minus 1. So we end up with 3 times x minus 1 plus 2x plus 8 over 3 times x minus 1 to the 1/3. Or if I simplify that down a little further, it looks like that becomes 5x. And then we have 3x plus the 2x is 5x. And then we have a minus 3 plus the 8, which is a 5. And we still have our 3 times x minus 1 to the 1/3 in our denominator. And so we don't really need to worry about the denominator because we don't really care about when the derivative is undefined for the second derivative test. All we care about is when the numerator equals 0, right? When the derivative itself is 0. So we just set 5x plus 5 equal to 0 to get x equals -1. And so we'll then go ahead and we will find the second derivative of this and evaluate it at -1. So our derivative here, right, f prime, we'll use that final simplified version. Our derivative was 5x plus 5 over 3 times x minus 1 to the 1/3, and we're going to find the second derivative here. So our second derivative should be the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, and 3 times the 1/3, right, just becomes a 1, so it just becomes x minus 1 to the negative 2/3. And then it's all over the denominator squared, so 3 squared is 9, and x minus 1 to the 1/3 squared will be x minus 1 to the 2/3. And so then we'll just take that and we'll evaluate it at -1. There's no real need to simplify it first, so we'll just go right ahead and figure out if this is positive or negative. So we have 3 times -1 minus 1, be -2 to the 1/3 power times 5. And then over here, we're just going to get minus 0, right, because 5x plus 5, if I evaluate that at -1, I get 0. And then in the denominator, we're going to have 9 times -1 minus 1, which is -2, to the 2/3 power. Well, in the numerator, we have 15 times the cube root of -2, which is definitely a negative number, right? The cube root of -2 is negative. And if I have down at the bottom the -2 to the 2/3 power, cube root of -2 is negative, but when I square it, it becomes positive, and when I multiply it by a 9, it becomes a positive. I don't really care what the actual value of this is. I know it's a negative divided by a positive, which is definitely less than 0, which tells me that the function's concave down, which tells me that I have a local max at x equals -1. Alright, back to a little bit easier one to take the derivative here. Our first derivative is going to be f prime of x is equal to 4x cubed minus 10x. We'll see when that's equal to 0. Right? Again, we don't care when it's undefined for this. So we'll factor out a 2 and an x, and that'll leave us with 2x squared minus 5. So we end up with x equals 0, and x equals, if we set 2x squared minus 5 equal to 0, that gives us 2x squared equals 5, or x squared equals 5 halves. So x is plus or minus root 5 halves. So then all we need to do is we need to figure out what our second derivative is. Well, our second derivative here is just going to be 12x squared minus 10. Okay? And so first of all, we'll evaluate it at 0, which is going to be -10. That means the function is concave down, which means we have a local max at x equals 0. And then we'll evaluate it at positive and negative square root of 5 halves. Well, if I evaluate it both positive and negative square root of 5 halves, I'm going to get the same value, right, because we're just squaring it. So let's do that. We'll do positive root 5 halves first. Right? That's going to give us, when I square the square root of 5 halves, that's 5 halves. So I have 12 times 5 halves minus 10. Well, that's equal to 20, right? We have 60 over 2 is 30, minus 10 is 20, which is obviously greater than 0. And if I do the same thing here, I have negative square root of 5 halves. That's also going to equal 20, because when I square negative root 5 halves, I still get the same thing. I still get 5 halves. So the function is concave up at those two values, so we have local mins at x equals root 5 halves and x equals negative root 5 halves. Alright, here we'll again take a derivative. F prime of x is equal to 5x to the 4th minus 9x squared. Only thing we can factor out of that is going to be an x squared. So when we set that equal to 0, we'll factor out the x squared, leaving us with 5x squared minus 9. Obviously the x squared is going to give us x equals 0, and this one will give us x equals plus or minus root 9 fifths. I'll probably prefer to write this as 3 over root 5, just because I can square root the 9, but it doesn't really matter if you do that. And then we'll find our second derivative here. So f double prime is going to just be 20x cubed minus 18x. And we'll evaluate that first at 0. And so f double prime of 0 is 0, which tells us that the second derivative test has failed us here. It tells us that we actually aren't going to have a max or a min there. We're most likely going to be having a point of inflection there. So we don't need to really worry about that. The second derivative test only works, like I said, at the places where the derivative is 0, but where the second derivative is not equal to 0, and clearly it is here. So now we'll find f double prime of 3 over root 5. So if I do that, we're going to do 20 times 3 over root 5 cubed minus 18 times 3 over root 5. And I mean, the arithmetic on it is, not something I necessarily expect you to be able to do super well in your head, but we can figure it out. It's 20 times, if I cube 3, I get 27, and if I cube the square root of 5, I get 5 root 5, and then we have minus 3 times 18 is 54 over root 5. Well, to figure this out, whether this is positive or negative, which is really all that matters, I just need to get a common denominator. So I'll put a 5 down there and a 5 here. Now the denominators don't matter, and it's really just like figuring out if 20 times 27 is more or less than 54 times 5. So our denominator is still going to be 5 root 5, but in the numerator, 20 times 27 is going to be 540, and 54 times 5 looks like that's that 270, right? 270. And so if I subtract that, that's clearly going to be a positive number. And so we could tell that, I'll write it up here because I'm kind of running out of room. If it's a positive number, it's concave up, which means we're going to have a local min at x equals 3 over root 5. And down below here, f double prime of negative 3 over root 5 is going to be, well, the same basic thing here. We're going to have 20, but it's going to be, when I cube the negative 3 over root 5, we're going to have a negative 27 over 5 root 5. Right? And then minus 18 times the negative 3 over root 5. Well, the arithmetic's all basically the same, except now the first number is negative and the second number is positive. Right? So we can see that this is going to be a negative value, right? The 540 and the 270 in the numerator are just going to swap around, which tells us that this function is going to be concave down, which tells us we're going to have a local max at x equals negative 3 over root 5. All right, and we've just got one more here to go for this. So first we'll just take our derivative here, f prime of x. Well, it's going to be 1 over x cubed minus 3x, right, because it's natural log u, so 1 over u. Then times the derivative of u, which is 3x squared minus 3. All we really care about is when the derivative is equal to 0. So f prime of x is equal to 0 when 3x squared minus 3 is equal to 0, which gives us x is equal to positive or negative 1. Now for this one we have to be a little bit more careful here, because the function itself, x cubed minus 3x, we have to think about what its domain is, right? So we know that x cubed minus 3x has to be greater than 0 in order to be able to take the natural log of it. So if I factor out an x from that, right, we get x times x squared minus 3, or x times x plus root 3, x minus root 3 has to be greater than 0. And if I make a sign chart with negative root 3, 0, and root 3 on it, I can test values in there. Like if I test 1, right, I get a positive times a negative, right? So anything between 0 and root 3 is not actually in the domain of this. If I plug in something more than root 3, like 1,000, I get all positives. If I plug in something like -1, I get a negative times a positive times a negative, which is positive. And if I plug in something like -1,000,000, I'm going to get all negatives. So we can see that our domain only goes from negative root 3 to 0 and from root 3 to infinity, which means that x equals 1 is not in the domain. So I don't really need to worry about that value. But I do need to worry about the value x equals -1. So what we need to do is we need to find our second derivative here and just evaluate it at -1. So our first derivative, I'll rewrite it, our first derivative was 3x squared minus 3 over x cubed minus 3x. So to find the second derivative, we'll just use the quotient rule. Right, quotient rule says denominator times derivative of the numerator, which will be 6x, and then minus numerator times derivative of the denominator, all divided by the denominator squared. And so we want to evaluate what is f double prime of -1, which was our only critical value. So as we go ahead and do that, -1 cubed is -1, and then minus 3 times -1 would be a plus 3, and then we have times a -6, and then over here, -1 makes 3x squared minus 3 equals 0, so that's just a 0 over there. In the denominator, it doesn't really matter what this value is, because I know when I square it, it's going to be positive. It ends up again being -1 plus 3 squared. Right? But we can see that what we end up with here is 2 times -6, right? -12 over -1 plus 3 is 2. 2 squared is 4. It's clearly less than 0, which tells us that the function is concave down, which tells us we have a local max at x equals -1. And that's the end of this walkthrough for our second derivative test. Remember, most important things are you have to find the derivative of your function and see when it's equal to 0, not when it's undefined. Check that those critical values you're getting are actually in the domain of the function, and then evaluate your second derivative at those x values. Remembering that if the second derivative is negative, the function is concave down, so you have a maximum. And if the function is concave up, when the second derivative is positive, right, you'll have a minimum. And that's it.